this is section 4.1, part 3 on videos for examples and classwork. So this one, we'll kind of do it together as an activity, but again, you can try at any point on your own. So we have this new car is valued at $20,000. It will depreciate to $17,000 in 1 year. If the value is decreasing linearly, so I'm going to tell you, well, let's assume this is linear. What kind of function would we come up with? What would it look like? And what would be the rate of decrease? So to figure out average rate of change or slope for a linear function, what we do is look at our points we have. So we have the new car is valued at $20,000. So that's time 0 and then 20,000. That's my y-intercept. So that's 1 point. And then I have 1 year. It would be 17,000. So that's my second point. Okay, so that's if linear. Okay, well, actually, that's would be for both situations. However, we're going to pop into y equals mx plus b for linear to show that relationship. So we need to find the slope. So in general, we always just do the difference. So we'd have 17,000 minus the 20,000 over the 1 year. Okay, 1 minus 0. And we would end up with a depreciation of $3,000 per year, right? If we wanted to write that as an equation, we could write it as the value of, we'll call it at time t equals negative 3,000 t plus 20,000 was our y-intercept. Now, it's different though if we have it decreasing exponentially. And again, these points up here, they're the same points, but now we're going to say, let's assume an exponential relationship. What is the annual rate of decrease? Okay, so this is going to come out a little bit different. We're going to have a percentage. So our base format is going to be, we have a b to the x, or we'll just call it y. Y equals a b to the x. B is our base, but we don't know what that is. That's what our question is. And how do we figure that out when we're given a couple of points to work with? So it's just kind of the same idea. We would just take and plug in values to figure it out. However, it's not the same as how we do the slope. We don't have a slope formula, but we do have points. So we have y that we can use up here as 1,700, 1,000. Our initial value is 2,000. 20,000. Gosh, I'm always off by a 0 here. 20,000. I want the cars to be cheaper, I guess. And then we have the B is the unknown that we're trying to find. And our X value that goes along with the 17,000 is 1. So we don't really even need to worry about that. So what we're doing in this case is we're actually just dividing. Okay, so then I don't have the exponent to worry about on that one, but it comes out to be my base is going to be 0.85. So that means my decrease, my rate of decrease is actually 100% minus the 85% would be 15% per year. So if this were a word problem, that's how it would be worded. So what's the, function? How would you write that if you had a decrease of 15% per year? Your base would end up being 0.85. So our equation that we could actually write from this would be V of t equals 20,000. Base would be 0.85 to the t. If the value is decreasing exponentially, when will the car be worth half its original value? So we haven't learned logs yet. If you've had those before, then you can maybe figure this out. That's how you solve for an unknown exponent, is using the inverse operation of exponents, which is logarithms, but we're not there yet. So we're just going to kind of do some trial and error, and you can get a rough ballpark. Another way you could do it is you could take this equation and you could put it into Desmos. So see if you can kind of figure that out. See if you want to play around with that and just do some trial and error. You could use Desmos or some other app. Okay, so trial and error, you would just pick some values. I might start with the value at 3. So I'm going to do V of 3 when t equals 3. So go ahead and plug that in to your function. So we would have 20,000 times 0.85 to the third power. Remember to do your exponents first. So just crunch those numbers and try that one, and then maybe try V of 4 and V of 5, and just kind of see what you get, and I'll meet you back here so you can pause and work that out, and then I'll pop my answers up as well. So using this method, we can see some trends happening. So that's one reason I wanted you to kind of work that out, get some practice, just noticing the patterns. And when your exponent goes up, your overall value is going down because you're having a decimal there, a number smaller than 1 or between 1 and 0 as your base. So we're shrinking, we're depreciating, and you can see how it jumps down quite a bit, So if you look at this, half the value of 20,000 would be 10,000. So it would be just over 4 years. We can figure that out precisely, like I said, using logs, but we can also graph that. So I'm going to do that. I'm just going to see what that comes out to be in Desmos, but I'm hoping that you're getting the idea of how these are related. When you have a base that's less than 100%, you're going to be decreasing in value there, especially because we just have a normal exponential pattern. Okay, so I put the equation in Desmos, and then I actually use the table function here. So you can use this little, here, I'll just redo it so you can see, but you just go ahead and type in your function, and then you get this graph, which is kind of hard to maybe read, but I blew it up. I found the 10,000 that I want for half, and then blow it up, and then I can pinpoint on there as well, so I can try to get a close That's not wanting to travel up for me. So right about there. So around 4.3 is our value. You can also use the table function here if you want to see. I can't put values in here. I can't put it won't allow me to, but I can put values in on the side too. So if you didn't want to do all the math that we did for the estimation, you know, you could start putting in some more precise values here. Whoops, it says 43. And get pretty close. So maybe, you know, I'm gonna say now that was a little too high. So it's like 4.28. And kind of go from there, and you can use that as a tool to get close. So at the beginning in this exponential, if I'm asking you to estimate a variable, you don't even need to be that. You could say between 4 and 5 or something like that. A little over 4 would be an okay answer. So that's it for part 3 of this set of videos from 4.1. There'll be one more. We're going to go over the last problem here with tables. So I just want to write the answer here. So about 4.3 here. So I'll just say. The last one we're going to look at, like, how do you know, given a table, if it's linear or exponential or what's happening with it. So it really lends itself to just crunching some numbers, seeing a pattern. So that's a different technique. If you want to try it on your own now and see if you can figure it out and come up with an equation for each of those without the video, and then just check with it, that's totally fine. But it'll take me a little while to go through it. So I'm going to do that separately. Have a great day.